As we mentioned earlier, light can be absorbed when it hits a particular surface, can be reflected off the surface, or it can move into the surface. And a lot of times all three are going to happen. We are going to discuss now the second thing that can happen to light, which is reflection. Due to conservation momentum, we are not going to get into it here, but due to conservation momentum, or let me just say, if you hit billiard balls on the sides of a billiard table, you'll notice that the ball is going to bounce at the same angle as it hits the edge. Now the same thing with light. Whenever a light beam is going to hit a particular surface, the beam that's going to bounce off is going to bounce off at the same angle relative to the surface. Usually in physics, we don't measure the angle relative to the surface, we measure the angle relative to the perpendicular to the surface, relative to the normal to the surface. So this is my normal, so the angle relative to the normal would be this for the incident or incoming beam. So the angle of incidence, which is the angle that the incident beam makes with the normal to the surface, which is drawn in blue here, is the same as the angle of reflection, which is the angle that the reflected beam makes with the normal. This is what we call the law of reflection. It's a very easy law, and it has very interesting applications. Okay, before we get into those details about the law of reflection, I'll show a few examples. Here it's an example of a picture taken by a student out of Warren Wilson College. What we have here, we have a laser beam shining on a particular material. I believe it is water, but I'm not sure. But notice what's happening here. I think this is a fish tank. So when it hits the water, part of it is going to be reflected. We are seeing the reflected part here. And part of it is going to move into the water. And then once it's going to hit the bottom here, part of it is going to be absorbed here by the surface, but the most important thing, part of it is going to be reflected. Notice here how it bends. We'll talk later on about that. The angle, the light here is not moving on a straight line. It is bending towards the normal. Here, the angle of incidence, the angle of reflection are the same. Here, it's not very visible, but the angle of incidence is the same as the angle of reflection. And you notice that the beam that's going to come out at the end is very much in parallel with the beam that was reflected here. This beam here, once it moved back into the air, it is refracted, bending away from the normal, and that's what we are seeing there. We'll talk about the law of refraction later on. But this is just to illustrate that both things can happen at the same time. And when you talk about reflection, sometimes there are multiple reflections like what we see here. Now, one more thing. These pictures here are from this website here. You notice the two pictures. They are not of the same location, but this one, we have a perfect reflection on the water of the mountain, and the grass and around it and so on. Now what happens is light reflected off the mountain is going to be reflected off the surface of the water, And that's the way we are going to see it or capture it on the camera. In this case, the water is a little wavy. Because the water is a little wavy, even though we have reflections, the reflections are not towards the camera here, and we don't see the mountain anymore. Okay, we'll explain that a little more. Notice this picture here. Notice it's the same picture. In the places where the water is wavy, we don't see much. Where the water is clear and not wavy, it's a very clear reflection. Same here, we don't see the boat because the water is being wavy here. We don't see the reflection because of that. Does the light reflect? Of course it has to, but we don't see it because it's not all reflected in the same direction. Okay. Now, to illustrate the point, I'm going to show you a couple of simulations here. Now, in this particular case, what we have, we are shining a laser beam, and we have a flat surface. So the angle of incidence is in red here, 18. The angle of reflection is the same angle, 18. And as I change the angle of incidence, the angle of reflection changes accordingly, the same way. Now, what if I have a surface that's not flat? Now, what does it mean, a surface that's not flat? It might appear flat like here, but microscopically, or even at a larger scale than microscopic, at a millimeter level or whatever, now the surface is not flat. What does that mean? When the light beam is going to hit it, this might be the normal at that particular point, what we have here in red. So what that means, as I move around, the normal at that point is going to depend on the orientation of that point. We still are going to have the angle of incidence is equal to the angle of reflection. However, that's happening at a small scale, and it's not as visible. And in other words, if I move it here, like last time when I was moving it, it was keeping the same angle. But here I have the incidence angle being the same, but the light is reflected at different directions. Okay. Let's go back to the previous one. Here, when I moved it, the angle does not change. In the other one, it was changing. Now, when we have a reflection of a flat surface, we call it specular reflection. Oops. Let's go back to the writing mode. We call it specular reflection. When the surface is not flat, we call it diffuse. So in the pictures we were looking at earlier, we have diffuse reflection here, and that's why we couldn't see the boat. Light is being reflected in all possible directions and not in the direction we were looking. Now, diffuse reflection is quite good because if all reflections were specular, you will not be able to see an object unless you are sitting in a particular location relative to that object. Now, what I'm saying here, if an object is here and your light source is going to come from here, if we have only specular reflection, you are going to be able to see it only if you are here. However, with diffuse reflection, if we are shining light here, we are going to have, we are showing only one beam, but we are going to have beams reflected in all directions from that particular point. Because of that, wherever you are going to sit, you are going to be able to see that object. So diffuse reflection is good. It's not good for the pictures we were talking about, but it's good here. Okay, we played with this simulation before, but I'll play a little bit more with it. Okay, remember, when we shine light over a surface, it's going to reflect only light at the same color as that surface. And if it is white, it's going to reflect all colors. And then notice how the light is reflected, and as depending on the roughness of the surface, we are going to get light in more directions. And of course, diffuse reflection in real life is going to be even more complex than this. The structure is going to be more complex than this, and you are going to get light in all possible directions, not just as the limited ones we see here. Okay, now the key point here, how do we see an object? We see an object only when light is going to reach, oops, go back here. We see light only, we see an object only when light is going to enter our pupil and make an image of that object on our retina. Unless the light is going to enter our eye, we are not going to see an object. We are not going to see the object. Now, when we have mirrors, for example, if I have an object like here in face of a mirror, now light reflected off the mirror is going to be reflected in all directions. If we take the tip here, it's reflecting light in all possible directions. Now, once it's going to hit the mirror, the light is going to be reflected according to the law of reflection. I'm not sure I'm doing the drawing correctly, but the angles are the same. Same here, it should be perpendicular. Angle of incidence is equal to the angle of reflection. Like for this yellow one, angle of incidence is equal to the angle of reflection. Now, what does that mean? These beams are moving towards the eye. They are going to enter the eye. This beam here is not going to enter the eyes. It's not going to matter to us. It's not going to matter to this eye. Now, however, for this eye, it's seeing two beams, and these two beams, they look like they're coming from here. So our brain is going to interpret that by thinking there is actually an image of the object here. And that's what we see. So the image is going to appear behind the mirror where there is nothing, because the light reflected off the mirror is going to look like it's coming from here. Now, just another application I would like to talk about before going on, rear view mirrors. Notice I could not find a better picture of a rear view mirror, but here's the one. Okay, now notice what we use to reduce the glare at night. We use that particular lever. Now, some modern cars are going away from that, but this technology started in the 50s, I believe, or earlier. Now, what's the idea behind that? This is our rear view mirror, and this is the lever. Now, what happens is we have two surfaces, a surface in the back, a surface up front. Okay, now light is going to be reflected off both surfaces. It's going to be reflected off the front surface or the back surface. And the idea of the lever is just to position the mirror such that the light reaching our eye is going to either come from the front surface of the glass here or from the back surface of the mirror here. One interesting illustration of this is here. Actually, I like this picture very much. It is showing us the glare here. That's at one position of the mirror. And then you reposition it and look where the glare is. And this actually, it looks, if I recall correctly, from a 1950 newspaper article.